So hi folks, my name is Matt Thomas and I just want to thank you for tuning into the USGS Landslide Hazards Program seminar series. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We typically wait until the end of the presentation to take questions, but you can enter them in the chat window ahead of time so that your questions are waiting to be answered at the conclusion of the talk. In the meantime, please just do your best to make sure your microphone is muted and your video is off when you aren't intending to speak. Thanks. I'll let you take it away, Francis.
Well, hi, everyone. I'm really excited to be able to introduce Dr. Paul Santi today. Paul got his start at Duke University, where he majored in geology and physics. And then he went on to Texas A&M and got into the practical side of things with geologic engineering, and went to the Bay Area, and which is sort of the mecca for landsliding and kind of geotechnical problems, and really spent a good amount of time getting a sense of the wide variety of geological problems that people face on a practical level. He came back to Colorado School of Mines to do a PhD, and then from there went on to Missouri S&T, or at the time it was Missouri Rolla. Taught there for a few years, and then Colorado drew him back to here, and so he's came back to mines to be a professor. He has been the president of both AEG and GSA, the GSA Environmental and Engineering Geology Division. He's also a GSA fellow. Recently, Paul has started the Center for Mining Sustainability. That's taken him to Peru pretty frequently, and he's gotten good enough that he's actually even giving talks in Spanish now, which is really impressive. But the really important thing to know about Paul is that he's an Ironman triathlete, and he has a really, really high endurance level. So not only is he a good scientist, but he can outlast just about any of us. So anyway, with that introduction, I'll turn it over to Paul.
Thanks, Francis. I'm a lot older than that now, and I have zero endurance, so I'm not going to challenge anybody. But thanks for the opportunity to come and talk to this group. This is a great group. I've had to miss a lot of the talk because I often teach on Wednesday afternoons, but I love the lineup, and I'm proud to be part of that. And so what I want to talk about today, I'm going to focus mostly on really a couple hypotheses that we explored and wanted to support regarding water and sediment supply for post-wildfire debris flows. And there's a couple questions that we're trying to answer. I'll also talk a little bit about kind of what things look like for the future, and some modeling we did looking at climate changes. And by we, I mean other people. These two students that are listed here, Blair McCauley, who got our master's a number of years back and works for Baseline Water in Calgary, and then Zane White, who just finished in August with his degree. And so I'm presenting their work. I was their advisor, which means I had some opinions, but I'll say that they did the lion's share of the work. And if you have any really difficult questions, you're going to have to ask them. And so I can dish things off to them. And so really what we're after here is I want to sort of adjust at least how I think about debris flows, and maybe how all of us. And I think there's an implicit model that we don't often state, but it's this idea that a debris flow is triggered, that we start out with a dry situation, dry soil. It starts raining. Once we have enough rain, a debris flow lets go. And I think that's true for debris flow intensity, but I want to kind of demonstrate that there's more than enough water in the system. And then the second part of the implicit model is that there's a finite supply of debris, and this idea that a debris flow kind of cleans out the channel, and you have to have some time for the gun to reload. And this is actually, I didn't use those exact words, but it's an implication that I made when I did my master's thesis in Utah, like over 30 years ago. And it was not a fire-related debris flow that wasn't quite as much of an issue then. But it ended up being an important point, and I would get a call every few years from somebody in Davis County, Utah, saying, well, there was a debris flow in this channel. Do we need to worry about it, or is there no supply left? And we've seen a challenge to this just in Glenwood Canyon the last couple months, when we get repeat flows in the same area. And there's this sense like, when will it end? It's every time it rains, there's enough debris for this. So that's sort of our implicit model, and I think we can tweak it a little bit, and I think it will help us when we consider the hazards for post-wildfire debris flows, to say, first of all, there's ample water before and after the debris flow, and it starts raining, there's water running through the system, then there's a debris flow, then there's more water running through the system, and we're not waiting to have enough overall to cause an event. But we are waiting to have this sort of intensity burst, and then the second point of that is that the sediment supply is ample and it can produce multiple events. And I would guess that most people that deal with post-wildfire debris flows probably agree with this hypothesized model and have said a lot of these things over the years themselves. And we're just trying to provide some backup for that and some data to say, yes, here's what you can rely on to show these. So where does our data come from? The rainfall data comes from a series of debris flows. There are 44 of them that occurred in 9 different burned areas, mostly about 15 or more years ago in Colorado, California, and Utah. A range of drainage basin size. The average is about a square kilometer, so these are not huge basins. But there's a few that are very small and a few that are very large. And then for each of these 44 events, we know the debris flow volume, and we had some detailed rain gauge data. In the rain gauges, some were right there in the same watershed, some are nearby. Maybe we had to do an inverse distance averaging of a few different gauges. There are obviously changes in rainfall with elevation and all that. So, you have to kind of squint to use the rainfall data, as always, if you're going to use it to represent what's happening over an entire basin. And then for sediment supply, the data that we used is distributed over the Pacific Northwest and the Western U.S. Had a pretty large database of events, broke into 3 categories: recently burned areas that are sort of actively recovering from a burn. So that means within, let's say, 1 to 10 years after a wildfire, and then some unburned areas or areas that have had more than 10 years since a wildfire. So then the model that we looked at was really two systems. And we said, okay, first of all, in some of these drainage basins where there were post-wildfire debris flows, there is unburned ground. And so maybe the fire only covers 60% of the basin or something like that. So we're calling that unburned area. We're only worried about the soil and saying there's some absorptive capacity for the soil. We're not really worrying about water percolating through the soil and into bedrock and considering bedrock as part of the model. And on a short time frame, like one rainstorm, it probably makes sense just to consider the soil portion of it. And then in a burned area, we're saying, yes, there's ash on top of it, and that's sort of there's a permeability contrast between the ash and the soil, and so we're worried about how much water the ash can absorb. We also made assumptions of horizontal topography, even though these are steep places that might have less soil where it's steep, but that the conservative assumption is to say the water velocity and all of that we're going to ignore. We're just going to say water hits this and it can either absorb or not on the basis as if it was flat topography. The ash thickness, we assumed about 10 millimeters. And this is there are some other people that have modeled this same thing. There's some people that have done some field measurements. We felt that was a conservative but realistic estimate. And then for the porosity, as the absorptive capacity of the ash, we assumed around 20 to 30%. And people have measured much higher, and that's usually almost immediately after the wildfire. But it compresses pretty quickly on its own, or if you get a little bit of water in it, it compresses. And so again, we wanted to have a sort of a realistic sort of average value. So we used 20 to 30%. Then we assumed when water hits the ash that there's 100% saturation, that there's no transfer of water from the ash to the soil because of this permeability contrast. And then once the ash is saturated, there's runoff. And so this is the fill and spill model that several people here have published papers on. And again, that's going to be our assumption for this water balance. And then there's this idea of antecedent moisture. How important is it whether the soil has some moisture content or preceding rainfall? And we didn't consider this, and I'll address it later in the paper or in the presentation. I think we've got some evidence that it's not a real strong factor here. And then finally, for unburned soil, and we'll get into this, but we're assuming that the infiltration can be modeled using some Soil Conservation Service, NRCS, runoff curves. So what that leads to then is the water balance equation, and this is really what we're after. And so on one side, on the left-hand side, is the input to the system, and that's the rainfall. And really, we're looking at a volume of water. How much storm rainfall was there times the drainage basin area? And so the total rainfall over this period of time that caused the debris flow times the drainage basin area. So that's the input, and then on the right-hand side is all the places that water can go. And we said really there's three groups. The first is it could be incorporated into a debris flow, and we can measure that. It can infiltrate into the soil or the ash. And then the remainder, the leftover, is the overland flow. And we wanted to look at the balance of this. And for the hypothesis that I'm proposing here, I'm saying that once you account for the infiltration, once you account for the debris flow water, that there is a lot of water left over for overland flow. And that fits the model that says it's raining, there's water running through the system, then you get a debris flow, and there's still water running through the system. So this is how we would estimate rainfall based on nearby rain gauges and so on, size of the basin. Debris flow water, we said, okay, we've measured the volume of debris in a number of different events, 44 different events, and we have to make an assumption of how much water was incorporated into that volume of debris. And we've used some rules of thumb that people have used over the years and said it ranges between 20 and 40%. And the 20% says we're not using very much water, so the leftover, that's the overland flow, would be sort of the high end of the bracket. And 40% water, that lower row, would say that's the maximum amount of water in the debris flow, so that's the low or minimum overland flow. And so we're using those to bracket the ranges. Ash infiltration, again, we're saying there's a porosity range in the ash. There's a high and low porosity range. The thickness of 10 centimeters times the burned area within that drainage basin. And so that assumes that any place that burned and was marked on the maps as burned has ash present, and any place that was not burned, the ash is missing. And obviously there's going to be some different situations there. The ash thickness might not be consistent, but we said that, just for practicality, we're going to make these two assumptions. Unburned soil infiltration is a little more complicated, but again, we went to the NRCS data. For those of you that understand it or have used it, we assumed an antecedent moisture condition 2, which is not bone dry, but it's not saturated. And we said it's fair to say there's a few percent moisture content. Maybe not the day after the fire, but within a few weeks or when most of these debris flows occurred. We picked a range of hydrologic soil groups to cover this area, and these are they're a little different depending on whether we were dealing with slides in debris flows in Southern California or Utah or Colorado. So we sort of matched it to the climate. But it shows a pretty wide range of textures and infiltration rates. And again, we want to say, is this a problem if you make an assumption that there's a broad range of properties? And then finally, for hydrologic conditions, we took a range from, again, for unburned, a pretty low percent ground cover to sort of a medium percent ground cover, which makes sense for the drier part of the western U.S. And then basically what this allows you to do then is select curve numbers. From curve numbers, there's a basic equation that you can use to calculate what the potential retention in the soil is. And then having that number, you can calculate what the potential runoff is. And so that P sub E is the potential runoff. That's the number that we're including in our equation. And then left over from this is overland flow. So that's the unknown that we want to look at. So the results for this then, here's a set of diagrams. And this is for the low flow. So this says we're putting as much water as possible in the debris flow, and the remainder is the overland flow. The three colors in the graph then, the bottom bar, the blue one, is how much water from a rainstorm, the percentage of water at that basin that would be incorporated into the debris flow. The red bar in the middle is the percentage of water that would infiltrate under sort of a maximum infiltration condition. And then the remainder is the green. And so what you notice here is there's only 4 of these that really wouldn't have any runoff under these conditions. There's a few more that would have a very little runoff, but the vast majority of these, there's a lot of green on that graph. And so that says you can look at how much water the debris flow would incorporate compared to how much water came out of this rainstorm over, typically a couple hour period, but sometimes it's multiple hours. So that's the low flow. Here's the high flow. And so this says we're not putting as much water into the debris flow, we're not infiltrating as much, and you can see there's even more green. And so I'll toggle back and forth between these, and you can kind of get a sense of what the range is. But to me, every now and then data works the way that you want it to. And I looked at this, and we plot the graph, it's like, that's great. To me, that makes a really strong point that there's excess water in this system. And so another way to look at that, we said, instead of 20 to 40% of the debris flow being water, let's pick the mid-range, it's 30%. And I want to know how much of the rainfall is incorporated into the debris flow. And that's what this bar chart shows. And the median is 5.7%, which is 1/17 of all the water is incorporated into the debris flow. And so again, I think that supports a model that says it's raining, there's water running through the system, then there's a debris flow, and then there's more water. So we're not limited by the amount of water. We're not waiting for enough water in the system before this happens. And so there's this idea of rainfall intensity. This is not really a new concept, but I want to show some data that we have from the Great Sand Dunes National Park, basically to show how important intensity of rainfall is as opposed to the total amount of rainfall. And so the upper two graphs are from 2 different drainage basins. We put pressure transducers in the channels. And so we could record then there's a little bit of pressure as water's passing through it during a storm, and then it jumps up pretty high when the debris flow comes over. So we really have within about, I think we were on a 15-second interval. So we know, within less than a minute of when the debris flow occurs. And that's the red arrows and the timing. The bottom 2 graphs are the rainfall intensity. And so the rain gauge for basin 24, I think, was 10 meters away from the transducer. And so this is almost an exact measurement of rainfall versus debris flow. Basin 16 was less than a kilometer from the transducer in basin 32, about the same elevation, so there weren't really orographic issues. But what you can see is that basin 24, there's a few little peaks in rainfall, and then there's in the middle of that graph, there's sort of a larger peak, and that thing ends, and within maybe 2 to 3 minutes, you get a debris flow at 510. And on the right-hand side, those 2 graphs, there's 2 debris flows, and you can really see the correlation between the rainfall intensity peak, and again, 2 or 3 minutes later, there's the debris flow response. Like I said, we're not the only person to do this. Here's some data that Sue Cannon had from years ago. These are cumulative rainfall graphs instead of just incremental intensity. So wherever the graph is steep means you have an increase in rainfall intensity. And then the blue triangles are the timing of the debris flow that came through. And so, again, you can see a really close link. I picked 3. She had in this study, I think there were about 10 different ones. I know other people at the USGS have measured the same sort of thing, and I think outside the GS as well. And then one other interesting thing with rainfall intensity, and if you've worked with debris flows, you've seen these graphs, intensity, duration, threshold graphs. And so each line here represents a series of measurements at a different drainage basin or different area. And so what someone does in that area is you're measuring rainfall, and sometimes there are rainfall events that don't cause debris flows, and other times there are rainfall events that do cause debris flows. And so for those 2 different groups, you can separate out some different duration intensity pairs and plot those on the graph. And so on the upper part of your graph, you have a whole bunch of X's where you say these combinations cause a debris flow. And on the lower part of the graph, you have a bunch of circles, and you say these combinations did not cause a debris flow, and you draw a line in between them, and that's the duration intensity threshold. And so there was these have been accumulated by people over the years, and then Sukan and Jerry DeGraff published this version where the gray lines are the thresholds for non-fire-related debris flows, and the colored lines are thresholds for fire-related debris flows. And what you can see is that it requires a lot less rain to cause a debris flow in a burned area. And those lines are a lot lower. So the intensity duration pairs are much lower. Again, this is nothing new, but to me, it shows that there's a rainfall intensity link that's easier to achieve the threshold after a wildfire. And then I've added a couple lines on here. The black line is what we measured at the Great Sand Dunes. And there were, I can't remember, I think maybe 4 different basins that had debris flows. And so we had a number of storms. And again, we put in a pretty solid line. It's right there within the group of burn basins. Great Sand Dunes was a little unique. Even though we were up in the mountains, there was a high component of wind-blown fine sand that had come from the dunes up onto the residual soil. And so that changes the character and the kind of erodibility and the hydrologic response of the soil up there. And so that's probably why that line is a little lower than kind of the average threshold for burned areas. And then the black dashed line was our basically the threshold that we established over the next 2 years of measuring. And I make it a dash because no debris flows occurred during the next 2 years. So the first year after the wildfire, there were at least 4, I can't remember the exact number, and we drew the solid black line. And then for the next 2 years, we monitored this, and the watershed, or the various watersheds, had really recovered, and there were no debris flows, even though we were getting stronger rainstorm events. And so that dashed line kind of represents the maximum, and so we know the true threshold is at least that high, and it might be higher. But it was really cool to see this much recovery and change in sensitivity to rainfall intensity just within a year or 2. So as I promised, I'll talk a little about antecedent moisture and how important is rainfall ahead of time in causing, in allowing a debris flow to occur. And so what the data shows here, the left-hand column, I've basically listed the names of several different fires that we were working with, and there are a number of drainage basins for each fire. And then I have a number 1, number 2, number 3. Those are different weather stations. And so we tried to sort of bracket this fire by picking weather stations at that were obviously nearby or within some of the drainage basins, but at different elevations so that we could account for any orographic changes in the rainstorm. So for instance, the first few rows, the Old and Grand Prix fire in California, it's a pretty big area. We're looking at all the drainage basins, and we use 3 different weather stations and so on. And so Then the second column, the middle column, just says, which drainage basins that had debris flows are we talking about? Are we comparing this to? Then finally, the right-hand column is really the meat of the information, and there's two parts of that. There's how much rainfall occurred in the entire previous week at that weather station, how much occurred in the entire previous month, and these are millimeters. And so what you can see in the previous week, the most we had was 5.6 millimeters, except for the Molly fire in Utah that had a little bit higher. So, again, millimeters it's not a huge amount of rainfall, but for the vast majority of these, this is half a centimeter within a week. That's not saturating all the ash and all the soil. And if you look at the previous month, I highlighted in red anything that was greater than 50. And again, for most of these, it's less than 50. That's 5 centimeters in a month, spread out. There have been some studies that show that it takes a month or two for the system to kind of re-equilibrate after rainfall. And so you could have some residual effects here. But I think that, to me, this shows pretty strongly that you don't need a wet week beforehand and then a storm that causes a debris flow. You can have pretty much bone dry soil that has had very little rainfall, almost none in a week, and very little within the previous month. And you can still get a debris flow that occurs during the rainstorm. Next, I want to move on and talk a little about sediment supply abundance. And I've got a few different, I'd say nothing is 100% diagnostic, but I think there are a few different things, clues that sort of point to the idea that there's plenty of sediment in the system for these debris flows, and we're not running out of sediment. We're not limited by the amount of sediment. And so this first group, what I want to show you, there are two graphs here that I've been carting around for years because I love them. And the upper one, Western US, WUS, yes, less than 1. So that's recently burned areas in the Western US, less than 1 year. And the x-axis shows how many different data points we have, or the y-axis. And the x-axis, we're measuring debris flow volume, but we're normalizing by basin area. So cubic meters of debris per square kilometer basin, because we know that bigger basins can probably produce bigger debris flows, and we wanted to normalize for that. And then the solid black line, vertical line, shows the median value. So Western US, less than 1, median values 7,188 cubic meters per square kilometer. Then the lower graph is Western US greater than 10. So this is areas that either have not burned or they've had at least 10 years of recovery. And the median value is much less. And so the over on the left there, I'm saying sort of how many events are in each group. And then really what we found, that second set of bullets, is that when you normalize it for basin size, the data I'm showing here, debris flows are more than twice as big after wildfire within that first year as compared to unburned areas. And we're ignoring differences in rainstorm and all these other things. We're just saying, we'll look at two big data sets. Is it worse in burned areas? And assume the data sets are big enough that they're covering sort of the same range of conditions. And so the answer, it is worse. And so kind of comparing apples to apples and using this normalized for basin area. And then we used a cluster analysis to try to do even more normalization. And so that says we normalized for basin size, and then we took smaller groups that had similar channel length and basin gradient. So now we're comparing like Granny Smith apples to Granny Smith apples. And in that case, there's even a bigger difference. And I'm not showing the graphs here, but instead of roughly twice the size, burned debris flows are 2.7 to 5.4 times bigger. And so to me, what this says is that in a burned area, at least, there's, first of all, a lot of sediment in the system. Second sort of line of evidence is looking where the material comes from. And so we had a series of graphs. This is one of them. We had, I think, 54 of these, where I had grad students over a couple summers basically walk up the burn channel and measure cross sections. And so you can see on this right-hand photograph that you can see how much the debris flow has scoured out material. And basically, by measuring a cross-section across that, and then you can make some assumptions as to what the pre-debris flow topography looked like. And you can see where it's cut off there and where the grass ends. And so we could compare that to adjacent channels that had not failed. So we knew what the shape should be. And so we could estimate then what's the area that has been scoured out and multiply that by the distance sort of average to the next cross section. And so we can have an incremental volume between these cross sections. And so what this graph shows, every square there represents a cross section. And you can see from the top of the channel where it says distance down channel is 0, and then to the mouth of the channel, you can see the growth of the debris flow and how much material is coming from the channel. And we also looked at evidence of rills, of smaller gullies, of sheet wash, and based on some measurements and estimations, on average, we concluded that about 3% of the total volume was coming from those sources as opposed to the channel. And there's some basins that were larger than that and some that were smaller, but the median value was 3%. And so then, to me, this says there's a lot of material in the channel that's being eroded. Sometimes it's eroded to bedrock, but like in this case here, it removed a lot of material, but there's still a lot of sediment in the channel. And then finally, you get bank failures. This might be Rich Giroux from the Utah Geological Survey that spoke last week. But you can see that it oversteepens the banks, and then for a period of time, you're recharging this thing by bank failure. And then the third line of evidence, I would say, for sediment supply abundance is this idea that you can measure multiple debris flows in the same canyon. And particularly this figure on the left, you can see how it's eroded material and removed it, but there's still a lot left in there. Same thing on the right, there's some bank failures. Again, this is what we're seeing in Glenwood Springs right now, in Glenwood Canyon, is multiple vents in the same canyon. And so I took two different data groups. The top table is from the coal seam fire, 2002, and the Missionary Ridge fires, the bottom table, that's also 2002. It basically said for these different watersheds, so each row is a different watershed, when were there debris flows occurring? And I just put an X when there was a measured debris flow. And what you can see then for the coal seam fire, 6 of these 9 basins had multiple flows. In fact, as many as 4 or 5 flows just in that first season. Missionary Ridge fire, 15 of the 16 basins had multiple, and again, as many as 4 flows. And so you have a debris flow, a few weeks later you have another one, a few weeks later you have another one. And at least in this first period of time, it appears like there's an infinite source of sediment. Now, obviously, we'll clean things out of the system over a long time period. But for a short-term hazard, for the first couple of years, while you're still really sensitive to the rainfall and all of that, you just have to assume that there's enough debris available to cause a debris flow. So that kind of concludes those 2 hypotheses. I wanted to move on to the work that Zane did recently, and says, okay, we recognize this problem is bigger. It's really sensitive to rainfall intensity. There's more than enough water. There's more than enough sediment. What does this mean? What does this bode for the future? And so we looked at the Thomas fire, which occurred in 2017. You may recall in January of 2018, there were this horrendous number of debris flows. They flooded Oprah's backyard. This was the Montecito, California events. And I say the size of the fire there, it caused the debris flows caused 23 deaths, 200 million in damage. This grabbed the public's attention. And so we said, well, what would happen if this event was to occur in 2050 or 2075 in the future based on climate change? And Jason Keene and Dennis Staley had a publication last year that was really nice, talking about some climatic effects. And so we wanted to do something a little more sort of parallel, but more on a very narrow geographic scale. and look at this. And so we're going to say, okay, what would happen if this burned in 2050 or 2075? What's the difference in rainfall, and what's the difference in the debris impact? And so as far as sort of looking at the hazard and measuring the impact, we use the things that are in the emergency assessment page that the GS publishes and keeps updated. And there's two sets of equations. The first is likelihood modeling, and says how likely is it to have a debris flow. That's part of the hazard. And basically there's a bunch of variables in there. This is all empirical. And I colored in red the things that would change with a changing climate. And so the proportion of the size of the burned area, the peak 15-minute rainfall is going to change somewhat. If you look at the volume modeling, the second group of equations, there's the area burned can change somewhat, the rainfall intensity. And so these are factors that we're going to plug into this same model. And then we want to say, well, what's the climate model for the future? And there are a lot of different approaches. Basically, what we wanted to use is these representative concentration pathways, RCPs. And the two sort of end members that we looked at is the RCP 8.5 that says, we're not going to do anything. We're going to let carbon accumulate. We're going to let the emissions continue, not change the climate. This is the worst case scenario, which kind of seems where we're headed these days. And then we really thought the best case is the RCP 4.5 that has some moderate emissions mitigation. And so we'll follow these models, and as you'll see, there's not a huge amount of difference in the response. It's definitely visible, but we're going to have to do better than a 4.5, I think. For a lot of reasons, but also because of post-wildfire debris flow problems. And so a couple things are changing. I mean, obviously, as the climate's changing, the temperature's going up, and that's going to cause a change in the hydrologic setting. And really, sort of the general conclusion is that the climate's drier, but you'll have more intense events. And so what we're comparing this to is, at least for this location, the USGS used a design storm of a 15-minute 40 millimeter per hour storm. And then we used some equations that basically said, okay, for every degree increase in temperature, in average temperature, you would see intense rainstorms increasing by 6 to 7%. And this is a really tricky thing to model, but it just says 40% or this 40 millimeter design storm, how will that change over time? And so we use then the I'm not going to try to, no, I will try to say it, the Clausius-Clapeyron relation. And then we used a CalAdapt website that does some temperature projections for Ventura County. And so then in the tables on the right, the upper table, you can see the RCP 4.5 temperature increase over time, 2 degrees, and by 2050, 2.4, and 2075, a little bit more than that with the RCP 8.5. These are big temperature changes. And then again, 6 to 7% change in rainfall for each of those. That's the bottom table. And so our 40 millimeter design storm now goes up to 46 to 50 millimeters. So that's one thing we expect to change. And then the fire is going to get bigger. And people have suggested this in other publications that I've referenced there. Some of their changes we've plotted here in the different colored lines. And we picked a median value, which if you can see, it's the gray line that's right below the orange one. And so it says by the year 2050, the fire size would be expected to increase 54%. And by the year 2075, the fire size would be expected to increase 81%. So a typical fire is going to be bigger. We've been seeing this, right? Three of the largest 10 fires in Colorado occurred last year. And so we're seeing these bigger events. So because we have a bigger fire boundary, we want to know what are the drainage basins. And so we use this land fire system to do that. We only dealt with the larger basins, bigger than 2 hectares. Interesting to note then the current fire has, the way we calculate it, 1,736 watersheds. If you increase it by year 2050 to 154%, look at this, we have over 3,000 basins, 3,115 basins, and then increasing it even more by the year 2075, 3,500 basins. So there's, just from that standpoint, there's a lot more potential for debris flows because there's like there are more than double the number of basins that have burned. So using sort of our methodology in our drainage basins, we reproduce some of the USGS models. You can pull up their website right now and compare them. They're pretty close to similar. But there's the likelihood model. In this case, brown is the worst. There's a volume model, and you basically group those by intensity and produce a hazard model. And so this is what we're going to be working with is the hazard. It says this basin has the highest hazard, the red ones have moderate, and the yellow ones have lower hazard. So that's our comparison piece. So if we just look at change in rainfall, just say, okay, we're going from 40 millimeters to 46 to 50 millimeters. The left-hand graph shows basically what happened in 2017. The middle figure there shows what we would expect by 2050, and you can see there's more brown and a little bit less red. And then the lower right-hand graph says this is what we would expect by the year 2075, and you can see there's even more brown. These aren't really dramatic changes, but you can see there's a shift towards higher hazard just within that. And then we want to add on top of that the change in fire size. And so this shows in blue the 2017 fire boundary, and then if we expand it by 54%, that's the yellow. And if we expand it even more, so this is kind of rubber sheet expansion. If we expand it 181%, that's the year 2075. If the fire were to occur then, that's the red boundary. Couple things to note, there's on that sort of southwest side is the ocean, and so it doesn't expand in that direction. There's an unburned island in the middle that's based on the development and everything, and we more or less retain that the same way it was. But everything else stretches very evenly. And we also did the same thing with fire intensity, is taking the current fire intensity map and stretching it. And so it monkeys with the basins a little bit, but it's easier than doing this individually for 1,700 basins or 3,400 basins. So the results then from this, so this is rainfall changes plus fire size increase. And you can see, again, the left-hand lower left is basically 2017. The upper middle graph is the year 2050, and the right-hand graph is the year 2075. They look similar because when we stretch this thing out, it has like the boundaries are sort of mirror image. But if you look really closely at some of the features outside, you can see how this thing is getting bigger and it's incorporating more basins. You can summarize some of that. I don't want to spend a huge amount of time here, but basically what this shows, the rows, the top row is the likelihood, how likely is it to have a debris flow, and these are divided by like 20% ranges. So 5 represents the 80 to 100% chance of getting a debris flow and so on. So the top row is likelihood. The second row down is the volume classification. Third row down is adding those two. So that's sort of the hazard classification. And then the bottom row says we're going to take the hazard classification and sort of renumber it into 3 groups. And then each column shows a different rainstorm. So the blue, the left-hand column shows what happened in 2017. The middle columns are the year 2050. And then the right-hand column in red is the year 2075. And the point I want to make with this is you can see a shift towards the more hazardous zones. So there's more basins, but there's it's more likely to have higher hazard basins. And then finally, I want to show this comparison of the models. It's a little bit busy table, but I've outlined in a beautiful olive green what I think are the important rows. And so the top row, 2017, 40 millimeters, 100%, that's normal fire size, 1,736 basins, we've seen that. And here's the total volume of debris that would be calculated using this model, 11 million cubic meters, and 54% of the basins are high hazard. So the next outline basin I have is that 2050. You can see higher rain intensity, bigger fire size, 3,100 basins now, twice the debris volume, 60% high hazard basins instead of 54%. And then if we continue on these climate models and look at the year 2050, the fire's a lot bigger. There's more than twice as many basins, 3,559 basins. There's 28 million cubic meters of debris in this system, and you could scale that up from a damage and dollar volume as well. And more of the basins are high hazard basins. So to summarize those results then, by the year 2050, there's 75% more burned basins. By the year 2075, it's more than double. It's 105% more. The volume is a lot larger, and the percentage of high hazard basins is a lot higher. So then to conclude, putting all this together, even with pretty conservative assumptions, there's excess water in the system. Debris flow doesn't so much depend on reaching, this magical amount of water, but it depends on this intensity. And so the limiting factor for forming these is the dynamics of the pulse of water, and not the sediment supply. And then climate changes are going to multiply this hazard significantly.